Hello and welcome to our video session on innovative IT security technologies. My name is Ivan Gudimenko and I am an IT security architect and subject matter lead for confidential computing and self-sovereign identity at T-Systems Multimedia Solutions. In this video, we are going to shed some light on our vision how the family of innovative IT security technologies, commonly referred to as confidential computing, can be practically applied to pave the way for secure, privacy-preserving, and compliant cloud-enabling scenarios. Namely, we're going to present a proof of concept developed with our partners from Eperi and Scontain. The main goal of it was to demonstrate practical feasibility of running an encryption proxy within a secured memory area on several established public clouds, such as Azure and Google Cloud Platform. The secured memory area is often referred to as Trusted Execution Environment and is now available off the shelf as a feature in Azure and Google Cloud, with several further cloud providers aiming at adding similar functionality in future. Ready for our short technology peek with us? Let's go! In the European Union, the tightly regulated business sectors like finance, insurance, and healthcare fall under stringent regulations according to GDPR, General Data Protection Regulation. At the same time, the business-driven motivation for migration into the cloud often outweighs the IT security risks associated with it. To enable this, the solutions encompassing technical security controls addressing the novel adversary models are necessary. This trend is especially relevant in the domain of e-health, etc. The aforementioned technical security controls have to be developed in accordance with the adopted threat adversary model. In critical domains such as e-health, the threat model often includes the platform or infrastructure administrators who should be technically prohibited to intervene with critical workloads and gain insights into the processed data running at the managed platform or infrastructure. Also, the protection of code and data in use should be ensured. As a side note, it should be mentioned that the protection of data in transit and data at rest can be already ensured using certain established security controls, such as strong encryption, for example. One of the possible ways to address the aforementioned challenges can be achieved by leveraging the technology stack in the area of trusted computing. The trusted computing paradigm, and more precisely the so-called trusted execution environments, provides the means to isolate the application code and data from the underlying environment, with some prominent examples being smart cards and secure element of a smartphone. However, the challenge here is to transfer this functionality into the cloud setting and make it available at scale in major cloud offerings. Confidential computing addresses this approach. At high level, it considers a secure coprocessor of the underlying hardware as a trace anchor. The isolation features can then be leveraged in virtualized environments and are made accessible for cloud applications. By this, the separation of concerns is achieved. Admins do not have access to the isolated environments, but still can manage the platform or infrastructure. In order to practically assess this technology, we invited our cooperation partners from the cloud enabler domain, Dominik from Eperi, who builds cloud encryption software, and confidential computing expert Christof from Scontain, who creates a dedicated development framework, facilitating cloud application developers in leveraging confidential computing in a transparent way. I'm happy to welcome Dominik here. Hello Dominik, happy to have you here.
Thank you for having me, Ivan.
So Dominik, could you please explain the classic cloud enabler journey, please?
So at Eperi, we transform any public cloud into a private cloud. And how do we do this? We encrypt data before it's being sent to the cloud. That way, neither the cloud service provider nor any third party who's accessing the data may be unauthorized can have access to the clear text data, not to the encryption process and not to the keys. And that's especially important when talking about cloud service providers like Amazon, Microsoft, or also Salesforce.
Since Eperi Gateway focuses on cloud enablement, could you please tell us about the customer demand for cloud-only solutions currently?
Well, actually, there is demand for exactly that, because customers try to get rid of their own data centers when they move to the cloud. And that way, they also don't want that encryption process to happen on their own premises, and are looking for solutions where the Eperi Gateway, which performs the encryption, can also deploy it in some cloud environment. And that, in the end, needs to be secure as well.
Since we know that security is a process and it's never a static issue, what are the future challenges and current limitations in the domain of cloud encryption proxies that you see now?
Well, the biggest problem we see here is that the cloud service provider does not get access to the data, which is also our purpose. And that way we limit the cloud service provider in performing its usual services like backend logic, filtering, searching, AI-driven development. And therefore, we sometimes need to redevelop that process and this functionality on the gateway side. For example, for searching, filtering, sorting, we have functionality on gateway side. But in general, here the target of protecting data conflicts with the goal of using most of the functionality on encrypted data by the cloud service provider.
In the regulated environments or in critical environments, it's often a very important requirement that the gateway itself is also additionally protected against the, for example, platform administrators. Do you see it also in as the challenge in your case?
Definitely. That's the second challenge. We see that, especially in cloud-only deployments, we need to protect against the cloud service provider who is running and hosting the Eperi Gateway, the administrators, and any third party who could access the algorithms, the basically encryption process on the gateway side. And that's why we did that project with MMS to see whether SGX or other technology that's similar can help by protecting that.
I know that conventional computing had already been known to Eperi before you started the cooperation with T-Systems Multimedia Solutions on this specific innovation topic. Could you please shed some light on these activities?
Right. So what we did there is, with a big German bank, we tried to outsource calculations, exactly that backend logic that I mentioned before, to such an enclave. And back then the technology wasn't as advanced, and therefore we only had some calculation part running inside a secure enclave. Now we're able to deploy the whole gateway inside such an enclave and protect the entire encryption process there.
So on this note, what would be your motivation to further cooperate with T-Systems MMS, with us, on innovation topics in the area of computational computing?
Well, that's exactly the point. I mean, what we've seen here and what we will see is developments of those secure enclaves. That's never a finished product. It will always iterate, and we'll see further developments there that also we with the Eperi Gateway can benefit from. So the attestation is one of the basic functionalities of such an enclave, but also what AMD has added with the entire VM encryption basically is helping us on that sense, and seeing both of them merging further and seeing new versions of these platforms will help us.
Okay, great. I'm looking forward for our future cooperation. Thank you very much for your time today.
Thank you, same here.
Thanks. Hello, Christof. Nice to have you here. Thanks.
Thank you for the invitation. Happy to be here.
Could you please explain the main idea behind the confidential computing in a bit more detail?
Okay. So confidential computing is about encrypting your application, making sure that your application is secured and you can run it in an external environment like a cloud, making sure that you can outsource the administration of your application, but still make sure that you are in full control of your data, of your code, and all your secrets that are needed to protect your application. And so basically you have an encrypted region in your main memory space where you can load your application code, and only the application code can see it in the clear. So if your cloud provider is in control of the hypervisor of the operating system, they cannot look into your application. So this is a new way to protect your application from outsiders, from attackers, from adversaries, and in a way that you don't need to depend on the hypervisor or the operating system.
Okay. And talking of cloud nativeness of confidential computing, which cloud providers have this feature? What is your experience in this respect?
Okay, so there are several cloud providers that provide confidential computing. So there is, for example, Microsoft Azure. So Microsoft Azure provides SGX machines as well as AMD SEV, S&P machines. And there is, for example, in Europe is G-Core. So G-Core provides SGX machines, or OVH as bare metal SGX machines. So there are different cloud providers that actually have this technology that you can use right now.
Okay. Well, you mentioned Intel SGX, software guard extensions, AMD Secure Encrypted Virtualization SEV, ARM Trust Zone. Could you please explain the core differences and the availability of each technology?
Okay. So Intel SGX was one of the first technologies, and there it's really about protecting a service, an application. So you can kind of protect a single service, and everybody that is outside, all the code, all the operating system, all the scripts that you need for managing the system are outside the trust boundaries. So they cannot look into the application. While an AMD SEV is about simplifying, transforming an existing virtual machine into an encrypted virtual machine and running them in the cloud. And so there the trust boundary is different. So there you ensure that all the operating system is trusted by you, your application provider, and also the administrator that log in, you trust. And so in this way you have a different trust boundary than in the Intel SGX version. In the ARM Trust Zone, there is more about you have one zone where you can have trusted application that is shared amongst multiple applications potentially. You see that these days, say in phones. But the next generation by ARM, which is called Realms, will have a technology very similar to what AMD has. So that you have multiple virtual machines, they're all individually encrypted, and where you can move your existing virtual machines in an encrypted version.
Okay, great. And what are the main decision criteria to go for a concrete technology, in your opinion?
This depends on what you want to protect. So what is your threat or adversary model? So if you want to protect against all administrators, then you would go to something like Intel SGX. So if you look at the e-health domain, there you have to protect each service from all the administrators. So there you would go for Intel SGX. If you have an existing workload that is VM-based, then you would use AMD SEV or Intel TDX, or in future then ARM Realms. But actually in future, hopefully we have something that is a combination of SEV and SGX, because you would like to have the Intel SGX technology to protect your service, and you want to have something like TDX or SEV to protect your VM, because then you can make sure that your application is protected against all administrators, as well as protection against the side channels, because if you control the operating system itself, you can make sure that there are no applications that try to do side channel attacks on your enclave, your SGX enclave.
Okay. Since you mentioned also Intel TDX, I would like to ask you about the maturity of these technologies.
So I think from the hardware, it's quite matured. At least the Intel SGX, now with the Ice Lake machines, you have lots of main memory that is encrypted. All the hardware is there, so they are protected. So they have for all the existing side channel attack or existing attacks, they have protection in firmware. From that perspective, they are ready to use. AMD, there they have the new technology which is called S&P, where you can isolate yourself from the hypervisor. This is also pretty mature. ARM is not there yet, so that will take a few years until Realms is available, at least to my knowledge. And so from that perspective, hardware is there. Software, there are some limitations. For example, in Intel SGX, right now there's no dynamic increase of the memory supported. The hardware supports it, but not the software. So this will take a few months until that is supported, and then you don't have to determine beforehand how large your VMs are or your applications are.
Yeah.
So you can dynamically scale up, and then you have less problems of knowing beforehand how much memory your application needs.
Okay, great. Development frameworks and dedicated middleware. So since you are an expert, especially for this topic, what is the motivation behind, please?
So if you have something like Intel SGX, you protect the application from access from the operating system. So that means you cannot perform system calls. System calls are needed to, say, write something to a file, to write something to the network. So you protect yourself from accesses from the operating system. That means you have to take care of the operating system calls in some other way. So therefore you need some middleware that helps you to run your original application and making sure that you can use all the features, the encryption features, and still perform your work. And therefore you have middleware to do that. And we have developed one middleware where we take your application in binary form, transform it, and then we encrypt everything that goes to the disk, to the network if you want to, and make sure that you attest your application. Because one of the main features of confidential computing is to make sure that you actually run in that encrypted region and that your code runs there before you give any secrets to your application, because you want to make sure there are no known attacks on your confidential computing environment before you give any secrets that allow the adversary to actually decrypt the files that you might have encrypted on your disk.
Do you mention remote attestation in this case?
Yeah, so remote attestation is, in my mind, or my opinion, one of the most important parts of confidential computing, because you can make sure that this application was not modified, that it runs in a up-to-date hardware, up-to-date firmware, so that all the attacks that might have been published have actually been addressed by Intel. And so therefore remote attestation makes sure we are on an up-to-date hardware, up-to-date firmware, our software is up-to-date, and only then, if everything matches, also the file system is in the right state and the application is properly configured, only then we provide the application with keys that allow the application to read actually the files, to have their access to their certificates. So in this way, remote attestation, in my mind, is the most important part of confidential computing. So
it could be used for secure bootstrapping
that
of the
is
enclaves.
Exactly. So typically you have this bootstrapping problem. So to get keys, say, from hardware security modules or HSM, I need to know something. And this, if the adversary gets to know these credentials to talk to the HSM, this adversary could also talk to the HSM. Now in confidential computing, my code is my key. So if I have a certain code, I can talk to others and get via remote attestation my keys. And so if somebody wants to impersonate me or my code, then they have to run exactly the same code, and so therefore it's actually my code. So therefore I solved that bootstrapping problem, how to get keys into my applications.
Okay, and the security backbone for this is Intel backend itself for the secure remote attestation? For
the remote attestation you have some attestation service. For Intel it would be the Intel attestation service. These days, actually, it's slightly different, so you can talk to, say, the Microsoft attestation service, but the certificates, so the root of trust, comes from Intel. Intel says, this CPU is actually one of ours, it's up-to-date, has the up-to-date hardware, has the up-to-date software and firmware, and then Microsoft uses that certificate to tell your key management service, yes, this application runs on inside of an Intel SGX enclave, it is up to date, and therefore, please, you are ready to give some keys to your application.
And what about AMD SEV or SNP in future?
So for AMD SEV, you have also attestation service. If you run on Microsoft Azure, you can use their attestation service for AMD SEV. There you have to be careful, so there are two versions of AMD SEV, or actually multiple versions. You should use the SNP, Secure Nested Pages, because then you decouple yourself from the hypervisor. So before SNP, the hypervisor must be trusted. After starting with SNP, you actually don't need to trust the hypervisor, and then you can attest that. You make sure that your virtual machine runs inside of a AMD SEV SNP machine, and then you can actually provision it with keys afterwards.
Okay, great, thanks. Talking about the development frameworks, about the dedicated middleware, which also you are working on, how do you assess the operations overhead to support the confidential computing middleware in production? For example, patching, feature update, etc.
Okay, so what we do is that we kind of one phase in the CI pipeline. So you have the continuous integration pipeline where you do your patching. And so what we do is we take your container image and have a binary transformation where we take kind of the newest version, transform it in a confidential version, confidential image. The files in the image are encrypted. We know exactly how to attest that application that you just created. We update the policy, and then you can use just the Kubernetes approach to update. So that means it's all transparent to your normal development process and also deployment process, because the only thing that you need is kind of one more step in the pipeline where you update the policy, where you update the image, where you encrypt the image, and then the rest you can use just the standard Kubernetes tools for your agile development method and continuous deployment.
And for automatization,
yes,
course.
Of course. You use yes, that is the goal, to automate everything. And since you can use all the tools, the different tools, whatever your favorite tool is, you can use to update your software.
And what about the licensing, end of life, and vendor lock-in in this matter?
So there, my view is that by having no changes to your application, so just having part in your CI pipeline, you have less lock-in, because you can transform your application, and if there's a different technology in 2 years, if you follow that approach, you have less lock-in, you have less investment that you might risk by having suddenly a new technology. So you just move this one piece, that is little effort, and that reduces your lock-in into certain approaches that you might have. So if there's new technology coming out from Intel or AMD, you just change that integration point a little, and then hopefully you can support the new hardware versions, new software approaches that you might have in the cloud in future.
So you essentially decouple the process of transforming the image or whatever is running there into a confidential computing way from the rest. Therefore, you can switch the transformation approaches in future in a transparent way.
Exactly.
Is what hinting at.
Yes. So the idea is to make that transformation transparent. So no software changes needed. So you take your cloud native approach, you develop with cloud native, you deploy with cloud native, and the only thing that you need to do is kind of the container image that you create is transformed one more time, and then you can use just all the standard tools to deploy that image, and underneath the hood then you do the attestation, you provide the application with the keys. The application is not aware that actually everything is encrypted on the disk. It might not be aware that things are encrypted on the network, so you can have a confidential service mesh, and that is all done transparently. So therefore you have no lock-in in that sense that you have to transform your development process. You don't have to transform your deployment process. So in this way you get actually a very simple start, and also later on, if there's new technology, you could replace that by a different approach.
Thanks. Coming back to the background security questions, how secure are these technologies that we have been speaking about, and how do you assess the vulnerabilities and known attacks? For example, SGX, SmashX, etc.
Okay, so there have been lots of published attacks. Some are realistic, some are less realistic. But we have to expect that any complex technology that we have, there are adversaries that might find a bug there. So we have, for example, we know that in Linux there are at any point in time 500 known vulnerabilities that can be used to attack Linux and hijack Linux. So there is always some danger, some risk with all the technology that we have, because we have millions of lines of code. There's always some bugs that could be exploited. And so the advantage, again, from confidential computing is that we can attest. So we can make sure that at least all the known attacks are addressed by our firmware and our software and our hardware. So that means we can have a enforced cyber hygiene, so we can make sure we have the latest firmware, latest hardware,
Control
latest
patching, such stuff.
patch. Yeah, and we can make sure that our software doesn't run in case it is not patched. And so in this way, we can actually address most of these attacks. If you are still worried about certain attacks, like side channel attacks, so Intel SGX was not designed for preventing side channel attacks. The assumption is that you do that in your application. And so in the Scontain framework, we have some randomizations that is at least in the development, what you could use to address some of the side channel attacks. The alternative that is, for example, used in the e-health domain is that you not only attest your application, but also the environment in which you run. So if you would have a combination of, say, SEV or TDX and SGX, you can make sure that you run in an environment where there are no possibility for side channel attacks. So all the programs that run there are known. They cannot be side channel attack programs. And you have the enclave where your application runs that is protected against all the administrators that might have access to your operating system, and all the programs that might run on behalf of the administrator. They are either authorized or they are detected that they are not authorized and they are prevented from running. So from this perspective, there are known ways of dealing with all these attacks. Remote attestation, the other is making sure that we have a clean environment where only authorized programs can run. And this way we can take care of these attacks.
Patching on the program level, as you mentioned, patching.
Patching is also important.
Defense in depth, so to say, as we usually try to do it.
Yes, exactly.
Okay, and since we also sometimes consider the questions in identity security, such as the fundamental breaks, so such technology can be fundamentally, inherently unsecure.
Yeah.
And how would you comment such statements with regards to confidential computing?
So, of course, there could be some attacks that break this technology for a while. But if you look at Intel, they expect that there are some bugs that they might have, and they have a way of upgrading the CPU. So you just give it new firmware, and most of the time you can fix these problems in firmware. So there's a little likelihood that it's a fundamental problem. If there would be a fundamental problem, so the idea is that we can have alternatives, in the sense that we might have a hardware-based attestation and a software-based attestation, or you have two different hardware manufacturers that provide you with alternative technologies. And so we follow the approach that we have policies, and so you can write in your security policy what kind of vulnerabilities you accept and which you don't accept. So all the security advisories, if you don't tolerate them, they will result during the remote attestation that your application cannot run. And so that means if you have two versions, one say for AMD and the other for Intel SGX, if there is a fundamental problem with AMD, it might not run on AMD, and vice versa. If there's a problem with Intel SGX, it might not run on Intel SGX until that is patched, and it will only run on AMD for that one. So from that perspective, we have some ways of dealing with that, because it has to be expected there will be more security vulnerabilities, and you have to have an approach of dealing with that.
Okay. Thank you very much for giving your insights on this, for shedding some light on this complex topic, and thank you for your time and for having me here. Thanks a lot.
Thank you for the invitation.
Please meet Kamal and Muneeb, who are responsible for the technical implementation of the proof of concept. Hello folks.
Hello.
Could you please explain what our innovation team practically did in this POC?
So our innovation team is actually working on this confidential computing area, and basically our try was to make this application, Eperi Encryption Gateway, make it more secure by using confidential computing technologies from Intel SGX or AMD SEV, and basically we tried to make it more secure using this confidential computing technology and onto the cloud.
And which confidential computing technologies were evaluated and why?
We actually used both the SGX as well as the SEV technologies from AMD and Intel. As you know, SGX is more of a container-based technology, and we have used it in more of like a single container as well as in the Kubernetes fashion. So, and we also tested the SEV in the same manner. But in SGX, we have done a full workflow testing, and the same has not been done in the SCV, but it works fine.
Okay.
No,
So we tested both Intel and AMD
yes.
technologies. And which target cloud environments have been used and why?
We have used the Azure for SGX and primarily used the Google Cloud for the SCV deployments. And in Azure specifically, we have used it for the Kubernetes, as well as for this in a single VM. We have deployed the SGX container in a single fashion, like in a completely isolated fashion. And in the SCV, we have used Google Cloud, but we have not done the workflow testing, as I said earlier, because of some restrictions in Google Cloud, as well as it was not deemed necessary because it was already done in the SGX incomplete. We just needed to see that if it was working fine. Although we also did some SCV testing in the Azure, but it was not in the production mode, so it was not something that we could have done completely. So we stuck to the Google Cloud for the SCV.
Okay. And in case of Intel SGX, which frameworks were used to facilitate the development?
So currently there are like many frameworks available for Intel SGX technology. Since it's pretty old technology, it's actually introduced back in 2015, and there are like lots of other frameworks as well, so like Graphene, Scone, Occlum, and many others more. But we chose Scone because it's in our opinion it's like the most enriched frameworks for this platform, because it actually provides the remote attestation out of the box, which other frameworks doesn't, and that's why we actually chose Scone for this purpose.
Okay. And in case of AMD SCV, which approaches were used?
In SCV, we used it directly. We just created a SCV based VM. So in a VM, you can deploy the Eperi as normal deployment of Eperi, so it's not much different than what we need to do. But in a Kubernetes fashion, we have created a finalized Eperi image and deployed it. And basically, we use the Google, and it provides a Kubernetes option for the SCV VMs, and the deployment was as a normal application deployment that you would do in a Kubernetes. But in this manner, we have a more secure application in SCV.
Okay.
And I would like to add something here. So basically, in the Google platform, you have the option to like add a confidential node for this SCV, and basically you have to provide the confidential node when you create the cluster, and that way you can actually use the CPUs from AMD EPYC second generation, which is basically providing you the AMD SCV technology, and then basically you will have to create the deploy it as a normal Kubernetes fashion, and it will be deployed automatically.
Exactly.
Okay, great. And which major challenges did you encounter, and how did you tackle them?
So there were some issues. So basically, at the time of this POC, Scone already supported Java, but the thing is, Scone actually supported Java from OpenJDK distribution, and this Eperi POC was actually based on Adobe JDK distribution. So there were some mismatches. So we had Scontain guys who actually fixed these issues for us, and thanks to that. And actually, other than that, there were some issues regarding the heap memory. So basically, this Eperi POC requires a large heap, and if we set it actually lower, then it actually crashes. So in case of this POC, it actually required at least 2 gigabytes of heap memory. Anything less than that, it would actually crash that system. And other than that, Scone also requires a large heap memory. Compared to the Eperi, it is actually pretty larger, I would say. It at least requires 8 gigabytes for this POC. Other than that, the system won't perform good, and this was some kind of issue.
In case of SCV, we also had some issues, like Google does not have the required stuff because it's still in the beta phase, the Google Cloud, and it's still working with second generation of the EPYC processors. So we had to do some workaround to do the whole deployment in Google SCV for the SCV, but as like in both cases, we deployed it successfully and tested it, and it was done as per our wishes. So it was pretty good.
The main obstacle with the Google was basically they do not provide any persistent volume with their confidential node currently, and this Eperi solution needs a persistent volume to configure its database management configurations. So that was like one of the hindrance for deploying it there and properly test it the workflow. But hopefully Google will fix this issue soon. And other thing is, like, we couldn't deploy it in the AMD SCV SNP, which is the latest generation, because Google does not provide it, but Microsoft Azure does provide it now, but it's still in beta phase, or I would say pre-production phase. So we are still waiting for their make it fully available for us so that we can test it there as well.
Okay, great. And talking about the lessons learned, please comment on the feasibility of this proof of concept for our future projects.
So yeah, overall it was actually a nice POC to work on. So we learned a lot, like what things could be done and what is currently the limitations. And but we think that in a nutshell, it is actually a very good solution for that purpose who needs more security on the cloud. Basically, we saw that whenever we are trying to like boot up the server, which is in the confidential manner, it takes a bit more time compared to the native one. But after the server boots up properly, the performance is not actually that less compared to the native one. So I would say it's more or less around 20% performance less. And I would say like for this kind of security, this is actually worth it. And we can actually try any other applications as well to make it more secure, who wants to make it more secure into the cloud.
All in all, we saw that this whole thing was very successful and it performed way better than we expected. And currently the technologies that we have their own drawbacks, but as soon as we get a new version of, let's say, SGX, they might be able to mitigate the side channel attacks as well, and it will become much more secure. And even in the current form that we have created, it's much more secure than the native applications, and the customers will be much more happy to have a more secure environment and to have the option to save their data from the cloud operators or any other administrator of the machine for which they don't have the access to. So I think this has been a very successful experiment on our part, and other than that, we are looking for the future technologies to make it much more foolproof.
Okay, great. Okay. Great job, folks. Thank you very much for your time and for having us here.
Thank you.
Thank you. Summing up, this new technology clearly has the potential to become state-of-the-art in the near future. It allows highly regulated industry sectors to benefit from the wide range of cloud advantages and to significantly increase the efficiency of the enterprise-wide collaboration. Even cross-border and cross-entity collaboration, for example joint analytics, with a minimum of manual effort for the line of business can be enabled. We hope you enjoyed our video, and we are looking forward to presenting our further achievements in the upcoming video sessions on innovative IT security technologies. Stay tuned and goodbye.